Hello, I'm Pedro, and this is the first lecture in a series on robotics perception, where I will cover the basics. I'm going to provide some context and discuss the core problems that it aims to solve. But first, I need to define what robotics perception is. So robotics perception is really a means to an end. Its goal is to provide an accurate estimate of the state of the world, including the robot, so that the robot actions can actually meet the planned goals. More specifically, perception and control are integrated in this classic closed loop shown here, where perception uses multiple sensors to continuously extract information about the world and the robot state as this changes, as the robot interacts with the environment. This loop is necessary because we don't have a perfect physical model about the environment that tells us what happens when the actions are taken. Instead, we might have a rough world model approximation in the planner or the control module, but that's really just a snapshot that diverges from reality as we project more into the future, and it needs constant update. So by definition, our environment is partially observable, so a camera can only see what's in front of it. It doesn't see beyond occlusions. And the environment is also stochastic, so events have randomness. So there's a random element to it, so we need to represent the probabilities of the outcomes. And I will cover a lot how we do this. So another point is that robotics perception overlaps significantly with computer vision. In my view, it actually extends it because it combines many sensors beyond your cameras. And a key challenge in robotics perception is how you know which of these sensors is lying. For example, a GPS may be working well, but then if the robot passes next to a tall building, it becomes unreliable, and we must then switch to another sensor, for example, an IMU or cameras. So the holy grail of robotics perception is to look for the optimal way to combine this, to combine information from these sensors. And this is called sensor fusion, and I will talk a lot about this. Another important aspect is that the sensor measurements are time-stamped, and sensors often have different frequencies. They're not typically synced, and so we must take into account the offsets between the sensor measurements. Whereas in computer vision, we might be dealing with a set of images which have no particular order. Now I'm going to illustrate this loop with an example to make things a little bit more clear. So suppose we have a rover on the moon, and there's no GPS yet on the moon, and we don't know much about the terrain so far. All we know is that we want to drive to the point B. And let's assume that we know exactly where the robot is at the initial starting point. We know exactly where it is, we know exactly where it's facing. So this is not really realistic. We always have a bit of uncertainty in the beginning for the initial pose. But let's just assume that that's taken care for the sake of simplicity. So we're just gonna go straight to planning. And for our planner, we just give it a straight line. So we have this straight line as a trajectory to point B. And now we are gonna send this to control. And the goal of control is to follow the trajectory by sending commands to the motors. For example, it will send wheel velocities that are converted to electrical signals. However, when we start driving, the wheels slipped a little bit on the sand, and the rover ends outside of the trajectory, more to the left side. So the goal of perception then would be to estimate the new position and direction of the rover, but also detect other things in the map, locate hazards, detect the hazards and map these, so that the planner then can feed a trajectory that goes around the obstacles. So the planner fits a trajectory around this obstacle from the estimated pose. So it doesn't collide with the obstacle. That's also a role of perception, to estimate the hazards. But the pose given by perception is only really an estimate. There's always error involved there. And in this case, I'm going to make this even more dramatic. So assume that perception was only using wheel encoders. We didn't have any cameras, so we are just using the wheel encoders. The wheel encoders measure how much you're rotating your wheels. And by measuring how much you rotate your wheels and because we know the geometry of the rover, we know the radius of the wheels and the distance between the wheels, then we can derive how much we traversed on that terrain and in where are we facing with the rover. But we didn't really model the slips, so we just think that we are along that line. So in the next round of planning, our planned trajectory is still going to be a line, but because the rover is actually here, we're gonna just drive straight along this line, and we might end up here at this point. And this error grows with the distance that you need to traverse, right? So the longer this distance you have to traverse, the higher the error. So this shows the impact of errors in the perception, especially early on. And what I'm describing here is part of a problem called the drift. What is the drift? The drift is this accumulation of errors that we have by integrating relative estimates like we did there. So we are integrating these relative measurements that have errors, and this causes an increasing error as we traverse that terrain. And so can we reduce this error? Yes, we can reduce this accumulated error by using absolute measurements. For example, we can detect map landmarks with the camera, and if we know that landmark in the map, then we can correct that error. But ultimately, the drift is something that we need to live with in robotics, so we need first a way to represent that error. The standard way is by using the Gaussians to represent the estimate, the uncertainty of that estimate. So in 2D, we have here on the right side this figure that shows the Gaussians as this ellipsis. And you see that the ellipses grow in size as we accumulate this, we integrate these relative estimates. And the shape of this ellipsis is parameterized by this covariance matrix here. This gives shape to that ellipsis. And if this is properly calibrated, then this is useful because then we can tell things. For example, we can tell that we are 99.73% sure that the robot is within a certain region. So that's very interpretable. Gaussians are very well understood and they're very convenient to manipulate. They're at the center of statistics, but they have only a single mode, a single mean. And that's a problem in certain cases. For example, more complex cases, let's say you have a robot in a corridor and we have an image of the robot and it's facing a door. So we know it's facing a door, and we know that in that corridor, in our map, we have two doors. So you would expect to have a bimodal distribution, a belief that it's either in front of one door or the other door, so nothing in between. And the Gaussian doesn't allow you to model this. One way to handle this is by using a distribution of samples. This is a much more flexible approach. We don't commit to a parameterized function for this. But they come with an extra computation, and in this lecture, I'm just going to stick to Gaussians for now. So so two practical questions arise here. First, how does the uncertainty actually grow? And then two, how do we update our state given incoming measurements that come at a different time with their confidence values? Now, for explaining the first one, for the sake of simplicity, let's consider here that the rover is moving along a line. So our state is two-dimensional. We have a position on that line and the velocity at that line. Now, we need to pick up a simple transition model that predicts what is the state in the future given the current state at time t. A reasonable model for this is a constant velocity model because of Newton's first law of inertia, so conservation of velocity if there's no force acting on it. This is reasonable for at least very short periods. So we can express, using this constant velocity, we can express the transition linearly with this matrix form, where A is the state transition matrix. And if we multiply the state transition matrix with this state here, the position and the velocity, what you see is just the motion equation. So it's very simple. But to represent the fact that this model is an approximation, we had a noise term called W. And this W is just a random variable that it's drawn from a Gaussian here, which has a covariance matrix that we call Q. And this is in detail that is important. It's going to come up soon. So to obtain the corresponding uncertainty of this propagated state in the future, so we have time t plus delta t in the future, we multiply A on both sides with A as transpose. And this is something that comes directly from the definition of variances. Or pointing out that the state transition was actually non-linear and not a linear function, but if this was a non-linear function, this second equation would be pretty similar, but A would be the Jacobian of that non-linear function. And that comes from first order error propagation. Now the second term is the Q matrix. The Q matrix is called the process noise, and this represents how much we don't trust the constant velocity model. It's just an approximation, and that's going to grow with time. So this covariance right here is going to inflate as time goes on, and we had this Q. So now we are at a position that we can propagate the state to any point in time and also its uncertainty. We can now answer the second question. That is, how do we fuse the measurements at the particular time when we observe the measurement? And now I'm going to make the explanation even simpler. Here the state now is just a scalar, and it's going to be the position, so we're going to drop the velocity. We have only the position, so instead of a covariance matrix, we'll have a variance as a scalar. And that makes things more easier when we have Gaussians. So before going there, we're just assuming that this variances P and R are just scalars. Right, so we want to know what is the state after observing the measurement, and that's answered by the Bayes rules. So we have the Bayes rules here, and the Bayes rules, here we are interested in the posterior, that is, what is the probability of the state given this measurement Z? And this boils down to just multiplying actually just two Gaussians. We have the prior one and the measurement one, which is the evidence. Importantly, this multiplying two Gaussians is going to yield another Gaussian. So keep that in your mind. Now this P minus is just the variance of the prior that we got from that propagation. And we have R as the measurement variance. And we are assuming that our measurement corresponds exactly to the state, which is often not true, but we are assuming that the measurement matches exactly the full state, so we observe the position. Otherwise, we'd have a function here, but for simplicity, again, let's assume that Z is observing X. So we have two Gaussians, and we removed the part of that Gaussian, so a constant part, because that does not affect the final mean and variance of the posterior. Now we are left with a multiplication of these two exponents, and we know that the multiplication of two exponents is just the sum of the terms that are inside. So after rearranging that sum, we do some rearrangement, and we can have this as a quadratic function with respect to x, and that's useful because then now this matches the Gaussian if we expand the square term. If we expand the square term, we end up with three terms. So we have the quadratic, the linear term, and the constant. We don't really care about the constant. But if we look closely, we'll see that this first term here and this first term here, we can actually get the P plus here. And the P plus is the variance of the posterior. So we obtain from the first term this P plus, and we see that the second term has the mu plus, which is the final state, so the state of the posterior or the mean of that Gaussian. And we can get that if we align this second term with this one. So after working a little bit the math, and you can pause the video and do that yourselves, and you'll end up with these two equations. one for the posterior variance and the other for the posterior mean. Now, if we plug the p plus here, so this term, if we plug it here, we end up with something that is much more intuitive. What you see here is that actually the posterior mean is just weighted average with their uncertainties as weights. So we're averaging this with the variance of the measurement, and this one with the measurement of the other. And so this is exactly what we expect it to behave. And then we have this normalization here. Right. So the mu plus is just really the weighted average with the variances as weights. And this, what I described so far, these are propagation. The propagation and the update is exactly what you see in a Kalman filter. So the Kalman filter is doing this recursively. So doing the prediction and the update part. This is a little bit more, the equation, especially on the update, complex, and that's because it generalizes to n-dimensional Gaussians. So the derivation is a little bit more complex, but it's pretty much the same, but with matrices. And we have h here, and the h is just because we have this this measurement model, and we're not saying that x is equals to z. There's actually a linear function of z with x, and that's included here as well. And so if we want to look here, the first term is called the Kalman gain. And the Kalman gain is then plugged here on the second equation. The second equation is doing all the work of giving the posterior state. And the posterior state is the prior state plus this innovation, which is just looking at the residual, so the difference of z with the prior mapped with this h here. And then there's a Kalman gain, which is really tuning that contribution there. The Kalman gain, if you look at that, you'll see the R here. So the R is the measurement noise that's drawn. It's the covariance of how much you trust that measurement. So there are two important knobs in a Kalman filter. There's the Q we talked about before, and there's the R. And when you hear something like tuning the Kalman filter, it would be typically fine-tuning these matrices here. So the Q is how much you distrust the dynamic model, whereas R is how much you distrust the measurement. And by tuning this, you can control how smooth your filter is, but it has some lag, or you can control how much responsive. So there's this trade-off that you have to tune, for example, in your controls to obtain the desired behavior. Right. Now, I mentioned several times the robot position and pose, but I need to be more formal about this so we can talk about this. So let's talk about the full 3D pose. So the pose is just, in 3D, is an element of the special Euclidean group, and it's special because of the rotation, you will see. It's basically just a transformation, 4x4 matrix transformation, which is comprised by the rotation matrix, which itself is a 3x3, and has this last column with a 1 here, and it has the translation vector. So the translation is really Euclidean, but the R belongs to the special orthogonal group 3, because it has some interesting constraints on it, and I will talk about this in a second. Right. With the SE3, we can do closed group operations. So we can multiply two transformation matrix, and you obtain a transformation matrix. And one way of seeing this is that we can obtain the transformation or the pose of this frame B2 with respect to the world frame by multiplying the TWB1, which is the transformation of the B1 with respect to W, times the transformation from B1 to B2. So we have here the relative transformation from B1 to B2, like I talked about before. So we have the relative estimate here, and we have the TWB1, and we obtain the TWB2. We can also see how this is useful to transform points. So let's say we see a landmark, a point here in P from B1. So we observed P in the frame B1, and now we can transform that if we know the transformation, the transformation from B1 to W. And so then we can express the P in the world frame just by multiplying with this matrix right here. As I mentioned, the rotation matrix has two constraints that makes optimization over rotations not trivial. It's also over-parameterized with 9 elements when the rotation only has 3 degrees of freedom. Now, for a minimal set of parameters, we have Euler angles. We can obtain any rotation by applying sequentially rotations around different axes, as we see here on the bottom. So we can we can do a rotation on X and then on Y and then on Z, and we multiply this in a sequence and you obtain any rotation matrix. Right, but the Euler angles suffer from critical issues. For one, they have a singularity. When one angle is 90 degrees or minus 90 degrees, the other two axes align and you lose effectively 1 degree of freedom. And that's known as the gimbal lock. Even astronauts in Apollo missions knew about this, and they were trained to avoid this gimbal lock configuration. On top of that, we can't do compositions or other useful operations such as interpolation and averaging with them. Another issue is about conventions, the order by which you apply the axis rotations in this matrix multiplication. So we can change the axis order, and in fact there's a total of 12 combinations. So that's because we have 6 when we use these 3 axes, so X, Y, and Z, so we can have combinations of 6. But actually you can do the same by doing rotation on the same axis as long as it's the first and the last one, and so you end up with 12 combinations. So that's really a pain to work with this. But we can also represent any rotation by a rotation around a vector, and that's called the axis angle, where the axis is just a 3D unit vector. From this parameterization, you get directly quaternions, which are very useful in robotics. We can perform integration with angular velocities, and it's very useful because the angular velocity can come from a gyroscope, and so you can integrate this angular velocity to obtain quaternions. We can also perform interpolation between measurements, and that's if we know it, then with this we can know the orientation at any point between 2 measurements of the quaternion. So that's also good for simulation and animation. We can also do direct optimizations we can directly optimize quaternions in a nonlinear optimization, but that's not the best solution, and that's because it has 4 parameters, not 3, and we need to deal with the unit norm constraint. There is a much more elegant solution, much more direct way, which is to work with a tangent space of SO3. But first, why can we optimize over a rotation matrix? Because nonlinear optimizers work by adding small steps, and adding small steps in the rotations does not give us a rotation. If we had 2 rotations, that you don't get a rotation because of those constraints that I mentioned. So instead, this addition needs to be done in the tangent space. Let me explain what I mean by that. The SO3 is a smooth manifold. It's a manifold projected here for visualizations in the Euclidean space. And a manifold is globally not Euclidean, but locally it is Euclidean, and it can be approximated by this tangent space. The intuition is for the tangent space of SO3 is that it corresponds to the angular velocity mapped to the identity. So it's not exactly the angular velocity in the body frame, but it's very close to that. So mathematically, it is this skew-symmetric matrix of this 3D vector here. And this 3D vector is just multiplying the axis of rotation with the angle that we already saw in the axis angle representation. So we can then go from this tangent space to SO3 by applying this exponential map from that tangent space. So the nonlinear optimizer then is just really updating that vector.